Surface integrals, very last topic, and we're just briefly starting surface integrals, and then in the upper level classes you finally learn how to deal with them. So we're just introducing you to this beautiful idea, and then you're out, and then if you take upper level math classes you learn how to actually do that. We will integrate a function over a surface. We've never done this before. A function over a surface. How amazing is that? We were integrating over the rectangle, over some 2D stuff, but we never did integrate over another surface. Again, you should understand, surface is a 3D object. Another surface is also a 3D object. So what is happening when we're integrating one over the other one? We've never done that before. So write down a definition. And the picture is very nice here. The goal is to find the volume of this solid under a function f. F is a 3D object. And over a surface S, which is also a 3D object. Think that it's the surface of the Earth. The surface of the Earth. This has lots of cool applications. But of course, as I mentioned before, you should be proud how far you went. To understand this, you have to go through the whole calculus sequence at least. Plus differential equations are mapping on top of these topics. This is want to find. Reminding you, want to find. So here is our mini parallelograms DS that help us. Let me explain previous topics, but the idea is actually it's a pretty cool idea here. So write down this. DS is the area of the mini parallelogram. Mini parallelograms are drawn on top of the surface. This one and this one and this one. Remember, we were approximating stuff with rectangles in Calculus 1 class, and you hated it. So in 2-dimensional, we were approximating with boxes. Now, how to approximate the surface? The surface is a piece of the material, right? And then you're like, it's kind of curved. It's nice to put tiny, flat parallelograms everywhere, and the smaller they are, the better they cover it, and it becomes shape. So let's do that. We're covering them like so. That's a very nice idea. In computer games, I showed you, I think in Zoom, you use triangles. If you remember, all your computer 3D games are built with triangles because it's easy to code it. But that's a computer scientist's choice. Usually, actually, parallelograms are very good. We know the area of the parallelogram is connected with the cross product. If you remember, cross product of two vectors looking like so and like so gives you the area of the parallelogram. So we'll be using that, the cross product of RU and RV. So idea, the base is DS. The base is full of those parallelograms. Looks very tasty for some reason. Then the height is F. Let's zoom out. The height is how far my F is. Oops, that is not a fixed. I should probably close this one. Oh, it's fine. The height is not fixed because the height is also a material. It's a function changing in 3D. So over here it's higher, over here it's shorter. But we do know that to describe the height, you just need to use F. The volume then becomes, just like in school, middle school, we know the volume of each box. Height times the base. So such a simple, elegant idea comes into 3 dimensions. Height times the base, which is F is the height, and base is DS, all those tiny, the smaller the better, mini parallelograms. When you sum them, you integrate. Remember, those are Riemann sums, and you sum them twice, because we're summing 2-dimensional objects, and that gives you double integrals. With F inside, DS outside, DS are tiny parallelograms. So if you rewrite it as a nice looking formula, in terms of parameter R, in terms of 2 parameters U and V inside of the R, that will be, you need to parameterize this function, and that's why we're teaching you to do that for this particular topic, in terms of R, which depends on U and V, times cross product, size of it. So we just need the size of that vector. Cross product of RU and RV, DU, DV, and those are parallelograms. So these are my cute looking parallelograms. They're trying to, like stickers, cover all the surface. The more the better, infinitely more. This is the height. Height times base gives you the volume. Collect all those volumes, approximate it like so, like on this picture. I'm going up, height times base. Height times base. Collecting them all in 3D gives you double integrals. So that is the idea. Sounds very complicated, and that is the case. It is very complicated. This is the same formula as the last time, except we have f ds instead of just ds. So let's work this out. There's so many people are sneezing. It's a bad time to get sick. Try not to. Drink hot tea and vitamin C.
Drink vitamin C.
Drink hot tea and do something to get vitamin C. Russians, we always drink when we feel like getting sick, tea with honey or no. Hot tea with honey, that helps your voice also. And hot tea with raspberry jam. So, that's also good. Write down the formula, don't get distracted. The example. Example 1. S is given as a cone in the first octant parameterized by. Luckily, the parameterization is given. Usually, maybe you're supposed to do it yourself. That's why we had the previous chapter all about. And then U and V are fixed. So, we try to get the picture. That is a cone. A cone is my surface. But we also have y. Y is the plane. So y is on top of everything. It will look like so. Not like so. It will look like so. Let me copy this. Because I'm afraid I will not do it as pretty as this one. Nice. We are trying to find this object. So slopes, you always start with the same. And that's why we were teaching you right now how to find the equation of a tangent line. Because we have the formula. The formula starts with slopes. So that's why we just did it so many times to find the equation of a tangent line. Step 1, differentiate. That's a nice beginning because at least you know how to do the beginning. Your brain feels good, that you're confident, you're doing well, and that's how you build confidence on a test or during your homework, and frustration hopefully goes away. Find derivatives with respect to u and v. Luckily, we are given with parameterization. Again, you're kind of supposed to do it yourself. So this is given, and this is like, yay. If you don't see it on a test, that's lots of work to actually parameterize it. That's what your homework is about, to learn how to parameterize surfaces. But okay, it was given. Let's differentiate with respect to u and differentiate with respect to v. I will not stop here for too long. We are very good in differentiating now. Like really good. So I will have cosine v, sine v in 1. And then the second one differentiating with respect to v, and that's inside of sine and cosine. So that will change minus u. Cosine becomes minus sine. And then sine becomes cosine. U survives. And then there's nothing at the end, so that gives you 0. Nothing with respect to v. Those are my derivatives. Why do we need them? Let's go back to the formula. One more formula to memorize. Yay. This is the tail I'm talking about. We found those partial derivatives. Now we need to find cross product and find the size of that cross product, the magnitude. So, Ru cross product with V is I, J, K. Plug in these components. Cosine V. Cosine V. Fine, let me make it bigger. I. Cosine V. J. Sine V. 1k minus u sine v, u cosine v, and 0. Nice. Luckily there's a 0 there, so at least something will be easy to calculate. And also you will have cosine square plus sine square, which gives you 1. So if you simplify that, it becomes minus u cosine u, comma, minus u sine v, no, it's all v, inside, change to v, and u. This is my normal vector. We don't really care about normal vector. The formula says find the cross product. We did it. Now just find the size of this. So step 1, we found derivative. Step 2, we found cross product. Step 3, find ds. ds is the magnitude of whatever you just found. So we know how to do that. A square root. It will be a square root. Square each and add together. As you can see, u squared cosine square plus u squared. Oh, don't forget to plus u squared sine squared gives you just u squared. I can write it down if you want, but you can ignore negative signs because it's squared anyways. We always do it actually, people who know it. You don't have to write down negative sign every time. U squared cosine squared plus u squared sine squared plus u squared inside of the square root. No need the parentheses here. U squared plus u squared plus u squared. No, u squared plus u squared. You factor out this one. Gives you 2u squared. So it's a square root of 2u squared. Or u square root of 2. That is the size of the cross product of those two vectors we just had. The magnitude, remember? And that gives you ds. Finally, only now we're getting into double integral. Finally. Step 4. But let me stop for a second. Does this look new? Because kind of all of this is the old material. The partial derivatives, we learn it. Cross product, we learn it. Magnitude, we learn it. Formula is new. Everything else in the formula is familiar. Even the double integral is now not new anymore. Look how far we went, that now we're not surprised to see just double integrals, not even triple. How lame. Double integral, the function y was given in the first place, and we found ds. So remember, this part over here is given. And now we can write it down. Double integral. So what is my y? I will ask you. I definitely know we found ds. That is my ds. Let me skip this place and write down u squared of 2. And don't forget to put du dv at the end. Du dv, because ds actually is du dv at the end. But what is y? And also s. S is important. S was given as a cone. Here it is. That is important information. R was parameterized. S as a cone in the first octant. Remember, it's only first octant. That gives you something important. And then it was parameterized by R, U, and V. U from 1 to 1, 0 to 1, V from 0 to 5 or 2. So, what is your Y? U sine V, how do you know?
Right there.
It's in the Y.
It's right there. I like it's in the Y's, exactly. It's right there. You're not supposed to say just right there. You're supposed to actually explain it. Imagine you explaining it to a blind mathematician. There was a famous blind Russian mathematician. His classmates actually helped him to keep going because he became blind during college. And then he became famous. Patragin, I think. Patragin, yeah. And he became full professor, published lots of books in math, and did some very breakthrough math research, being blind for the rest of his life. But his wife also helped him a lot, which is always underrated, to be honest. But she did a lot of typing for him, so yay for her. So as you said, it will be u sine sine v, thank you. Now, from where to where? What is my u doing and what is my v doing? Let's go back and check that. Again, you're supposed to build this. What is my u and v doing? But it was given. So, if v is outside, we're going to put 0 to pi over 2 outside. If u is inside, 0 to 1. But if you remember, since, I'll put it in blue, since those are numbers, you can switch to order of integration. If there's no functions, you are free to switch. Integrate each. Those are actually two integrals if you want to do it easier. It will be kick out the constant outside. It will be just everything with u is u squared du times everything with v sine of v dv. Oh, those are just two integrals. U is from 0 to 1. V is from 0 to pi over 2. Integrate each. Integral each. And you get square root of 2 over 3. So, lots of applications. Last 4 minutes to write this down. While you're writing it down, actually I will just have a nice screenshot. Applications, of course, with the density. We covered it before, this idea of that the objects don't have the unitary densities. Biological objects or physical objects might have liquids inside of your lungs are not the same as liquids inside of your bones. So, is today Bones Day or not? Does anyone check? Yes, you should know TikTok if you know what I'm talking about. Did anyone check if today is Lucky Day or not? But the idea is that densities are usually not fixed. And density does add a new dimension to the whole idea here. So if f, the function we just had inside, is your density, then this double integral gives you again the mass of s. So think like a metal of the metal plate or your body and so on. Again, f is density which might be changing throughout. S is over here, if we want to find the mass of the object, so we can do that. And again, double integral with respect to S gives you area of S. That's also one of the applications. Yes? Yeah.
No Bones Day.
No Bones Day? Oh, okay. No wonder. Okay, then let's work hard. That's what it means. If you guys don't know, it means it's a hard working day. But you should Google what does it mean. It's actually very cute. So that's kind of all for today. We're going to be suffering with this new topic for more 2 classes. Let me know if you have questions.